Here's a question about spread. How would you work out the spread of a data set? A data set of values that represents some variable that you've measured, for example the heights of everybody or their weights or their salary. You know the values aren't all the same. They are a little different about some kind of average, and you want to work out, give a numerical value to this measure of the spread. Any ideas? Well, it turns out we have a choice of ways of working out the spread, and the three most common ones I'm going to speak about today are range, interquartile range and standard deviation. You have probably heard of the first one and the last one. You may not know what the last one is, but you've probably heard of that. And this reminds me, this slide, that a common jargon word for spread is dispersion. The textbooks like to use lots of jargon words, so I will use them as translations, but I'll make sure that I always tell you what they mean as well. So let's start with the easiest one, and the easiest one is the range. Now if I've got a data set, the range as a measure of the spread is simply the difference between the biggest value and the smallest value. You take away the smallest from the biggest. So very straightforward. Let's see some examples. So here's a data set. I've got 1, 2, 3, 4, 5 values in there. The biggest one is 23 and the smallest one is 3, so the range must be 23 take away 3, which is 20. Let's do another one. This data set's got a much bigger spread. The biggest one there is 100 and the smallest is 2.1, so getting the calculator out, our range is 100 take away 2.1, 97.9. You'll notice something pretty quickly here, and that is that the range isn't going to be a value in the actual data set because it's not that kind of a measure, but also more importantly, the range as a calculation only uses two values from the data set. So in terms of its representativeness, it's a little questionable because you're only taking the max and the min, and if the max is what's known as an outlier, or even the minimum for that matter, in other words a value that is way outside the central region, then you might even argue that it's not a good measure. Let me show you one final one that might catch some people out. Here's a set of data values, and you notice that one of the values, the very last one, is -4. This might be, I don't know, temperatures in some physics experiment or something. Now to find the range here, I've got to take away -4 from 156, and those of you who remember that two negatives make a positive won't be surprised to find that the range appears to come out bigger than the biggest value. And it's a bit like saying if I went from 156 degrees down to -4, what is the centigrade change there? Well, it's a centigrade change of 160 degrees. So there we have the range, the most straightforward one, but not by any stretch of the imagination the most sophisticated. So let's look at the second one mentioned, the interquartile range. Now this one is very, very closely associated with our median that we measured in the previous video. So with interquartile range, the formula is that very, very helpful and confusing Q3 minus Q1. Where's Q2 gone, I hear you ask? Well, Q3 is known as the upper quartile and Q1 is the lower quartile. The missing one of Q2 is our old friend, the median, which we don't use explicitly, although it comes in to our working out. Let me show you how. So, work example coming up, here we go. So I've got a data set of several values, and as if I was working out the median, the first thing I'm going to do is I'm going to arrange them in ascending order. So let me do that first of all. So here we go, smallest to biggest, and the first thing I do is I split the data set in two. Okay, and this would be our median or Q2 if we were to measure that. We're not interested in that at the moment, but we kind of use the idea of that. Now you'll notice that because there was a 2, 4, 6, 8, 10, because there was an even number of values, there was an exact split where there was 1, 2, 3, 4, 5 in the lower, 5 in the upper half. The fact that Q2 we could identify as 14 doesn't come into it. The splitting of the data set simply causes a 50-50 split in the data set. So we now go ahead to find Q1. We find the median of the left hand half, the lower half, and Q3 will be the median of the upper half. So the lower quartile, which we're labelling Q1, there it is, we can just see by inspection it's the number 8, and the upper quartile, Q3, again by inspection it's 19. And now the final part is just like working out the range. It's the difference between Q3 and Q1, between the higher value of the quartile and the lower value. So it's 19, take away 8, which is equal to 11. So our interquartile range for this data set is 11. That's pretty straightforward with a small data set, pretty straightforward when the data set has an even number of values. Let's see what happens when instead of an even number of values you have an odd number of values. Okay, so let's run another example. Okay, so as before, been given all jumbled up, so I'm going to put them in ascending order. There they are. Split it in two, and this time because there's an odd number of values, my split is right through that number 17. That will be our Q2. Now, I don't know whether to put the 17 in the lower half or the upper half, so the way most definitions of interquartile range work is to say we'll ignore it. We'll just take that value 17 outside of our thinking, and so the values 0, 2, 13 and 14 form the lower half, and 20, 25, 31 and 34 form the upper half. So like before, we now find our Q1 and Q3, and okay, I have to do some thinking here because the lower quartile is somewhere between 2 and 13, which we get just by adding 2 to 13 and halving. And to get the upper quartile Q3, we'll add 25 and 31 and half that. We're effectively splitting the difference. I've written them as top heavy fractions, but I could have written them as decimals. 15 over 2, otherwise known as 7.5, and 56 over 2 is, I think, 28. Okay, and then Q3 minus Q1, there it is. Our interquartile range is 20.5. It's a lot more laborious than working out the range because you're not just picking out two values. You're having to do a little bit of work. And of course, if the data set got quite large, it would be quite a pain to find them. Of course, computer programs run that for us. It's merely the concepts I'm illustrating with you today. But that interquartile range, apart from its level of sophistication being different to the range, also you'll notice that the values Q3 and Q1 are numbers that are not the extremes. They are sort of deliberately coming in from the extremes. In other words, if we had outliers which were not representative of our group, they would not influence this particular measure of spread, this particular measure of dispersion. So it is a more sophisticated measure and therefore in many ways more preferable. Okay, now we get on to the big daddy of them all, the standard deviation, the one that you may vaguely remember from if you did higher at GCSE. It always sounds trickier than it is, partly because of the notation used. Let me talk you through an example. So standard deviation is a measure of the spread, a measure of dispersion, and let's imagine I've got the running time in minutes of 9 compact discs. There they are, and I'm thinking, okay, I can work out the mean just by adding and dividing, but how am I going to work out the spread? And this time I don't want to just select two values from there. I want to have every value represented, every value I want to play a role in determining my measure of spread. How can I do that? Well, first things first, work out the mean, and this way, in this case rather, it comes out to be exactly 58 minutes. It could have been a decimal, but I chose my numbers just to make life a little easier. Then what I do is CD by CD, find out the difference, or the distance rather, between that data value and that mean. Okay, so this is the value that's often referred to as the deviation. It's the deviation from the mean. So here's my data set, and term by term I look at the data set starting with 49, then 56 to 55, and just see how far each one is from the mean. Some are below the mean, some are above. The ones below come out negative, the ones above come out positive. But you see a whole bunch of values. It just so happens we didn't have any running time exactly on the mean. That's perfectly possible. If we had, that would have had a deviation of 0. Now at least we've managed to generate a set of values for each data point that has something to say about the spread, and I would now like to give an average of that, but I have a problem. The most common average we know is the mean, and to work out the mean you add the values and divide. But if I add those values in red, if I add those deviations, something really annoying happens. By definition, the mean of those deviations will come out to be 0. Therefore we cannot use the idea of the mean to find some sort of measure of spread. The negatives are exactly cancelling out the positives. So what do? Well, we could just ignore the negatives and say, okay, I'll just treat them all as positive. But that seems a rather ad hoc method. We need to find a method of getting rid of negative values. And can you think of one? Think back to school days. What operation did you do back in school with negative values that ended up giving a positive? Okay, well, one way of getting rid of negatives is to multiply them, to square them, to times them by themselves, because if we recall, a negative times a negative gives a positive. For example, positive 3 times positive 3 is 9, and also negative 3 times negative 3 is also 9. So we could square every deviation, and those that were positive remain positive, those that were negative would magically become positive. Okay, let's do that with our data set. So here we are. So I've got my negative 9 squared, my negative 2 squared, etc, etc. I work it all out, work the whole thing through, and I get a grand total of 274. What I've put in that line in red is an example of the sort of notation that kind of freaks us out, but that we do see in the statistics books. What you've got there is notation that gives you a symbolic way of representing your data set without actually having the data set every time. So x1, x2, x3, right up to x9 are labels that represent my first data point, my second data point, my third data point, etc. Now the other one, the x with a little line over it, we read that as x bar. And what x bar is it is the mean. It's the mean of the data set. So it will be x1 take away that 58, x2 take away the 58, etc. That's how we generated those deviations, and something like that is very, very common in the textbooks. But as I say, when you first see it, you just kind of think, I cannot understand this. It has a simple representation, but it does take some getting used to. Okay, but we've got 274. What do we do with that 274? Well, there were 9 values, but I'm going to have to divide it by 9 then. Just to finish that thought about the notation, the textbooks do one further step. In adding those deviations, they get a little lazy and go, is there a quick way of doing this? And use this capital Greek S, the sigma notation, to indicate summation. So that top line in red can be written more succinctly using the bottom line, and that reads as the sum of the deviations squared, the sum of each element's distance from the mean squared. You square them all and you add them all up. So the summation sign, the capital sigma, simply stands for add all the terms together. Okay, so I got ahead of myself there, but what we do is once we've worked out the sum of the deviations, which we did, we kind of want an average of that, so that's why we divide that by the number of values in our data set. We had 9 values, so our n would be 9. N is a very common value used to mean the number of values in a data set. So we have this curious object that we've worked out, which is the sum of the squares of the deviations divided by the number of values in our data set. And that particular calculation has a name. It's known as the variance of the set of data values. And we're kind of homing in now on our standard deviation, because to get from the variance, this object, to our standard deviation, we simply undo all that squaring. We just take the square root of that whole thing. So with the variance given there, the standard deviation is just a square root of the variance, and now we have that hideous looking object, which is the final thing. You would never have to work this out by hand, because we have calculators, we have computers, etc. You can run this kind of thing in Excel, etc. very readily. It's very straightforward to do. What's important is what this represents. It represents a measure of the spread where every value has contributed. Clearly those values close to the mean don't contribute very much. Those values further away contribute more, which is exactly what we want. We want a single value, a summary value of our data set, which gives some sort of an idea of the kind of spread that's going on. This is not the only measure of spread, but it is certainly the most common used. Now, just to add a little bit more confusion, this particular definition of standard deviation is not the only definition of a standard deviation. The one we just shown there is known as the population standard deviation, and on a calculator and computer programs you'll see there's Greek lowercase s, sigma n. Now the population standard deviation simply means I have got a complete data set of all values of interest. I have not taken a sample. So I've got my population. My population might just be my class of 30 students and their scores. I have them all, so I'm going to work out the standard deviation using sigma n. If I've got a class of 30 students and I choose to only use, say, 5 of them, I've taken a sample, then I have to work out something a little different called the sample standard deviation. called sigma n minus 1, which is almost exactly the same calculation, whereas the denominator, instead of being an n, is an n minus 1. For reasons which is certainly outside the scope of this video, this is then what you'd work out for the standard deviation, because what this represents is an estimate of the population sample, of the population standard deviation from which you have drawn the data. So you'll use a sample standard deviation to estimate the population standard deviation if you don't have access to the entire population. And this is common of most health related research that we come across. We interview a sample of the population, we measure a sample of the population, so we would use sigma n minus 1 as our calculated value of the standard deviation. So let's stand back and look at those measures. We started off with 9 CDs and 9 running times. We worked out the mean. I missed a hat there, missed a bar there. The mean was 58. We measured, if we were to measure our range, it would be 19. Our interquartile range is 8. Sigma n, which I didn't complete for you, but there it is completed, is 5.52, and for what it's worth, if we worked out sigma n minus 1, it's 5.85. I'm putting those values up, so if you did want to have a play around without a calculator, you can check your numbers. The crucial thing to notice is that those values are getting smaller. The range is by far and away the biggest value because it just represents the biggest and smallest values. The IQR, the interquartile range, as we know, takes values a little in from the highest and lowest, and that explains why it's smaller still than the range. But the standard deviation is kind of the distance around the central peak. So in many ways it's seen as the spread, if you will, of the central cluster of data. So there we have it. Standard deviation is the most sophisticated, interquartile range is of moderate sophistication, and range is the least sophisticated. But they are our most common measures of spread that you will see in research papers and textbooks. Okay, so in summary, data standard deviation is a measure of the spread of values in a data set about the mean value, and it takes into account all values and is the only one I've shown you that does so. Okay, so thanks for listening.